In our part 2 video for Module 3, we're going to be talking about statistical inference. This isn't the first time you've heard me say this term, but we're actually going to talk about what it really means this time. So now that we have a lot of our foundational information, you guys know what a mean is, you know what a standard deviation is, you generally know what a hypothesis is, the null hypothesis versus a research hypothesis. We can actually talk about how those things relate to what research is all about, and that is statistical inference. What are the things that we want to consider when we collect samples? In other words, what are good characteristics of a sample, or what characteristics should a good sample exude? Generally speaking, they should be randomly selected. Okay, so in other words, everybody has an equal chance of being a part of the sample, given that they have the common characteristics that the target population has, which would mean that our sample is also representative of the population of interest. Okay. Why do we collect samples? We can't always measure the whole population, right? So statistical inference is all about taking a sample, making sure that sample is representative of our population. That way we can generalize our sample results to estimate population parameters, which is statistical inference, right? It's inferring characteristics about a population. So inference meaning you don't know the exact answer, but you're inferring, or you're making a very nice educated guess based on sample statistics that you've already collected. Okay, so we're inferring characteristics about a population based on the characteristics of random samples taken from said population, right? So we're looking at generalizability when we look at statistical inference. In terms of sampling error, this is the amount of error in the estimate of a population parameter based on a sample statistic. So sampling error is usually valuable to know because it provides us with a way to determine how accurate the sample mean is and the odds that it is deviant from the population mean by a given amount. Sampling error is referred to several different ways in this class. Usually it'll be in the terms of standard error, but we calculate standard error for a lot of different things. So far you guys have seen standard error for skewness and kurtosis. That is part of the calculation that comes out in SPSS for your output, for your explore, your means, and your frequency analyses. We've also calculated it by well, not by hand, but we calculated it in Excel by taking like the square root of 6 divided by sample size, or the square root of 24 divided by sample size, depending on if you're looking at skewness or kurtosis respectively. Okay, so sampling error is telling us how much error do we have in our generalization or in our inference of our sample to our population, in other words. What we're going to look at primarily for this lecture is looking at the standard error of the mean. So you can think about standard error. A lot of people get standard error and standard deviation mixed up. In essence, they're very similar to each other. So standard deviation is specific to a sample, or if we're looking at a pure raw set of data, a whole bunch of individual scores that have been collected, standard deviation is going to be the distance of that score from the mean of that sample. If we have all of the values collected in a population, we could also have the standard deviation of the population, but generally we don't have this information. So standard deviation is going to be applicable when you have an individual raw score and you're looking at how far that raw score exists from the mean of that sample. Standard error is, if you think about a sampling distribution of the population. So remember we said a sampling distribution is where we have a bunch of sample means that we've collected from a bunch of different samples, right? And we plot those sample means on a distribution. That generally should create a normal shape. Standard error of the mean is, let's say, if we take one of those sample means, similar to a raw score or an individual score within a sample set of data. Okay, we take that sample mean and we say how far is that sample mean from the population mean. If we know the population mean, we can pretty well figure out what that distance is. Oftentimes we're going to have an estimated population mean. So sometimes we'll say, well, what's the difference of our sample mean from the estimated population mean? That's where our sampling error comes in, right? We're seeing, again, I'll just go back to this slide, right? We're looking at how much error do we have in the estimate of a population parameter based on a sample statistic, which is exactly what we're doing here. We're taking a sample statistic or a sample mean, and we're using it to see how far away we might be from a population mean. So standard error is a way that we can evaluate sampling error. Okay. The formula that we can use to figure out the standard error of the mean is standard deviation divided by the square root of n, or our sample size. We reduce standard error by decreasing sample variability. So think about your proportional laws in mathematics, right? When you have a numerator moving in a certain direction, so let's say in this case we decrease the variability in our sample, we decrease the standard error of the mean. Similarly, if we increased our standard deviation or increased our variability, we would increase the standard error of the mean. So in this case, when our variability changes, we get a proportional variation in our standard error measurement. The other way that we can reduce standard error is by increasing our sampling size. Okay, so oftentimes you guys will see like, oh, that's a small sample. Increased sample size is often a limitation that's noted, or a small sample size is the limitation that's noted in research, especially if there's less than 30 people. And this would be an indirect relationship or kind of inverse proportion, right? So if n increases, if the denominator increases, that means we're dividing by a larger number. Therefore, standard error would go down. Okay, so n increases, standard error goes down. N decreases, standard error goes up. In terms of which of these we can manipulate, sample size is going to be the easiest. You can always add more subjects. You can't always control their deviation, right? Because these are raw measurements that we're taking in real time. What we already talked about, manipulation of data is a no-go in research. So whatever the standard deviation is of what you have measured is what exists. You can't usually control that, but more often than not, you can control how many people you have collected within a given sample. Okay, so usually we want to reduce standard error simply because we want to make sure that our estimate of our population parameter is as accurate as possible. So the less error we have, the more accurate our estimation of the population parameter is. When we create a sampling distribution, again, just to give another visualization, we've taken a bunch of random samples. So each of these little plus signs is going to be a sample mean, right? And when we plot all of these sample means onto or into a frequency distribution, we should end up getting a sampling distribution of the mean, which we've already talked about, right? And so we end up with a relatively normal curve, which should exist for a sampling distribution of a population. So within all of these sample means, we usually can have an estimated population mean, right? Where are the bulk of our means kind of congregating around, or what value do they congregate around? From there, we can create a confidence interval. So a question for you guys, when we have a normal distribution, what measure or calculation can we use to find the probability that a certain score will land in a specific area? Right? So if you said z-scores or in units of standard deviation, you're on the right track, right? Remember that standard error is kind of the same to standard deviation, but instead of looking at the distance of an individual score to the mean, we're looking at the distance of a sample mean to the population mean. Okay, so kind of using similar principles, we can find the probability that any random sample mean will land within a certain area of our distribution. And the area that we generally estimate that this population mean would exist in is what we call our level of confidence or our confidence interval. Okay, the area outside of that level of confidence is going to be what we call the region of rejection. Generally speaking, your estimated population mean is going to be based off of your sampling distribution, so all of your sample means. Where you're estimating that is going to be within a confidence interval that is set by a certain level of confidence. And whatever is not included in that estimated interval is going to be your region of rejection or your alpha. What is a level of confidence? Level of confidence, I'll just refer to this as LOC in terms of abbreviations from here on out. But basically, this is the percentage that tells you if your null hypothesis is true. Okay, so it has to be based on characteristics of a normal distribution. So assuming that our sample distribution is relatively normal in comparison to our sampling distribution of our population. Within our level of confidence, we have noted that the population mean can be estimated to exist within that interval, right? So if we take a random sample mean or a random sample and we have the mean and we plot it, it should relatively exist within that interval if that sample did truly come from the same population. So the way that we can calculate our levels of confidence is by looking at the area under the curve or the probability, right, that we are going to get a value within a certain region of our normal distribution. So if I go back to this slide really quick, you can see that our confidence interval or the area of our level of confidence is mutually exclusive to where alpha exists. And all of this is going to be equal to 100%, which is how we represent levels of confidence, is in percentages. So we can say 1 minus alpha. Usually alpha is an a priori or set previous to the statistical analysis. So we take 1 minus alpha, which is usually denoted as a value between 0 and 1. And then we can multiply that by 100 to get the percentage for our level of confidence. On the flip side, alpha is our probability of error. So its actual notation is alpha. Most of the time, you guys are going to see P related to alpha. So P values, P stands for probability. The actual P is calculated based on characteristics of your sample. Alpha is set a priori. So alpha is a non-changing value. P is calculated or a changing value based on your sample characteristics. So I do want to make that distinction. They do not represent the same thing, but they are compared to each other when you are going through your hypothesis testing. So alpha is going to be the probability that you make a type 1 error. We'll talk about what type 1 actually means later in the lecture. But another way you could phrase this is that alpha represents the probability that you are wrong, right? Or that the null hypothesis is incorrect due to chance or occurrences that are not controlled. So generally speaking, if you land within your region of rejection, that represents how much error you're willing to accept, or how much error could be included if your results are significant, right? So when we look at the effects of some type of intervention and we want to know if that intervention actually worked, we need to have a very, very, very small chance of error that is included with the results of that intervention, right? The less and less error that we have, the more we can attribute our results to the effects of whatever our intervention is. So, well, again, I'll talk about this more. This is a concept that is really difficult to grasp for most students, so I try to say it a lot of different ways. But you can see that when we calculate alpha, it is 1 minus the level of confidence. So these are really easy to calculate. Subtraction. Woo! Okay. Level of confidence is represented as a percentage. Alpha is usually presented as a decimal. Percentages between 0 and 100. Decimals between 0 and 1. So an example would be if we have a level of confidence of 90%, right? You could easily calculate alpha by saying 1 minus 0.9 or 100 minus 90, and you get 10% or 0.10. More common to most of you is a 95% level of confidence, which has an alpha of 0.05, and a 99% level of confidence, which has an alpha of 0.01. Okay. 95% is kind of the most common level of confidence used. The reason why we say 95% we'll discuss a little bit later when we get to the hypothesis testing, but in a nutshell, what this means is you're 90, or that percentage amount, right? You're that confident that the estimated population mean lands between two distinct values from your sample.